Hi, thank you everyone for coming out today. My talk will focus on how to ensure trust and understanding in machine learning systems. There's been a recent book by an executive at Microsoft, someone who's worked in the industry for a long time, called Tools and Weapons. And I think that's a very apt phrase. So I prefer the term machine learning over artificial intelligence because most of the time, if we see artificial intelligence today in the world, it's machine learning. But machine learning, just like any other technology, can be used as a tool or a weapon. And I think one of the main things that we can do to ensure that machine learning is not used as a weapon is to establish human trust and understanding in machine learning. So I'm going to put forward a framework for how to do that today. This is what we'll be talking about. It's a fairly technical framework for how to accomplish these goals, and we'll move through a workflow in stages. But before we get to the workflow, let's just talk about a few things. So I'm lucky enough to be able to work with some of the leading researchers and practitioners in the field. And this workflow is based on many people's input. It's not just my own work. I think that's always important to say. And can I get the timer, please? So another thing is this term human-centered machine learning. So I would say that human-centered machine learning is a term that I'm also not trying to cannibalize. It's not a term I'm trying to steal or say that I made up. It's a term that has been established already in human-computer interaction literature. And I think some of the techniques that I'll discuss could help further the goals of human-centered machine learning from a technical perspective. OK. So this is the blueprint. This is how I think that you can establish trust and understanding in machine learning today. We're going to work through each part of this blueprint. Some stops will be quick, very quick, because luckily some of these things are very easy, and they're just things that we need to stop and remember to do. Some of them are more difficult and more involved, and so we'll spend a little bit more time at different places in the workflow. OK, so first is understand your data, OK? Machine learning learns from data. And I hear a lot about biased models or incorrect models, and that's certainly something we want to avoid. But most problems in machine learning actually come from the data. The algorithms don't learn anything that's not in the data. So typically things like unwanted sociological bias are present in the data, and then they're learned by the machine learning. So it's very important to just understand what's in your data. The way these slides work, and hopefully you'll have access to them after the conference. If not, please come see me. I'll get you the slides. The pink writing is a link. It's a piece of open source software. It's totally free. You can use it today, and it's just something interesting that I thought people might be interested in. It's a piece of software for sampling large data sets, specifically for data visualization. Because a lot of the best data visualization tools don't work with large data sets. And this is a piece of open source technology that will sample big data sets, leaving in a lot of the important attributes so that you can use it in your favorite visualization tool. And then I've also tried to provide some references if you're interested in any of these topics so that you could follow up more later. OK, so very quickly, these are two of my favorite data visualizations. I like them both because they show us a lot about a data set, but just in 2 dimensions. So people love to talk about big data today. And I'm actually have never been a fan of big data, but one thing is true, that big companies and governments do have a lot of data, and they do need the ability to work with large data sets. And one issue with large data sets is when you have many columns, many dimensions in your table, it's very hard to see, right? Because people can only see 3 dimensions at most. So we have to come up with a way to show a lot of information in just 2 dimensions, or maybe 3. I actually prefer 2. I don't think I have very thick glasses. I'm not particularly good at seeing things even in 3 dimensions. So I really want things in 2 dimensions. The visualization on the left shows the relationships between the columns in a data set. So each node, each circle in the graph is a column in a data set. And the thickness of the line between them shows their Pearson correlation, or the strength of their relationship. The colors come from a graph community algorithm, or the colors mean that these particular columns are somehow related to each other even more strongly. So it's a very nice way to summarize how the columns in a big table are interacting with each other. And that's one of the things that a machine learning model is good at learning, how the columns interact with each other. The other visualization is what's called a projection. So that takes the rows of a data set, no matter how many columns it has, and projects it down onto just 2 dimensions. So much like you can see my hand is a 3-dimensional object, right? But I can see the shadow of my hand on the wall back there. So that's a projection of my hand into 2 dimensions. So what you're seeing here is a projection of a large, well, it's not a large data set, a projection of a 784-dimensional data set onto 2 dimensions. And I can see basically all the rows in the data set. And so when I can see all the rows in a data set, I can look for things like clusters in my data, or sparsity, the lack of data, which is actually a very problematic thing in machine learning. I can look for I said cluster, sorry. I can look for hierarchy, right? Are things inside each other? And I can look for outliers, rows of data that aren't like other rows. So again, I like these techniques because I can see high-dimensional data in just 2 dimensions. Okay, so this is one of those easy ones. You just need to record what you're doing, right? Scientists always recorded what they were doing in a notebook, and I don't think that's such a bad idea. You can use a laptop if you want. How will you know if the next model you train is actually more accurate, or more secure, or more fair if you haven't recorded where you started? So just take notes. Just make sure you know where you are and if you're actually improving. Okay, feature engineering is the process of taking an original data set and the columns that are in that data set, somehow combining them or enhancing them so that they present information in a way that's more suitable to the machine learning algorithm. We have all kinds of options when it comes to feature engineering. Now, some of these options take the original columns and actually obfuscate them, make them harder to understand. I don't think that's a very good idea for high-stakes decision-making processes. So I want to make sure that when I'm massaging my data to make it more consumable to the machine learning algorithm, I retain understandable columns in my data set. Because later, when I go to explain my model, very oftentimes those explanations are based on the names of the columns or the meaning of the columns. And if I've used something like deep learning to extract features, I may have made the columns of my data set extremely difficult to explain and understand. So we want to remember to retain interpretability in our feature engineering processes. Okay, so another sort of sidestep that we can think about is we now have the ability, when we're doing the feature engineering process, to account for things like security, privacy, and fairness. And I think it's just something to be aware of. And there's trade-offs, right? Sometimes when I try to make a system more secure or more fair, it may have negative outcomes in other aspects of the system. So I think I just want to make sure that people are aware that there are many methods. If you're concerned about privacy, GDPR, it's a big thing, then you have options today to pre-process your data to help ensure privacy when the machine learning model is used. Because as we'll talk about later, the machine learning model can be attacked and hacked, and the training data can actually be extracted through the model endpoint. Okay. So another very exciting thing today in 2019 that we can talk about that maybe we wouldn't have been able to talk about a few years ago is accurate but also highly interpretable machine learning models. So things like GA2M or scalable Bayesian rule list, these are relatively new inventions that allow for very complex and accurate model forms that are also highly interpretable. And in fact, I might go so far as to say that for tabular data, for regular data that you can look at kind of in an Excel spreadsheet, the idea of an accuracy interpretability trade-off is dead. So there's no more need to use a black box model to get a more accurate fit to tabular data today. We have always tried to assess our machine learning models. And measurements like lift and AUC and average squared error, these are important. And it's important to look at these when we're training a model. So this is a step that people have always done. I think we should keep doing it. I think residual analysis is a particularly effective type of traditional model assessment that we should keep doing. I think the one thing to keep in mind is that things like, or measurements like lift and AUC and MSE, they don't tell you anything about whether your model is fair, about whether your model is secure, about whether your model would experience runtime errors when it's deployed in a IT system. So these types of traditional assessment measures are important, but they're also woefully insufficient to tell you if your machine learning model is actually workable as part of a large, complex IT system. Okay, explanations. We're gonna spend some time here. This also, say, is a relatively new innovation. Maybe really hit the scene in 2016. We now have the ability to do what we did for a long time with more traditional linear models, to say, for any one given person or piece of equipment or whatever the entity is that forms a row of your data set, we can say exactly why a machine learning model made the decision it made in regards to that one entity. Okay, and we call that, some people will call that process explanation, and I think that's a fairly good name for it. One leader in the field wants people to call it summary explanations because they can be a little bit approximate. I can agree with that. I think that's okay. Probably the two most famous methods are called LIME, Local Interpretable Model Agnostic Explanations, and there's a link to it there, and Shapley Values, and we'll talk about Shapley Values more in just a minute. So, one thing I'm highlighting on the slide is there has been some criticism of explanation, and I think that's important to address for a moment. So there was a paper written by a very brilliant researcher called Stop Explaining Black Box Models for High-Stakes Decisions. And I think my take on this is someone who has been working on explanations very intensely for several years is it's very important to pair explanations with interpretable models, okay? Or at least constrained models. Say something like a monotonically constrained gradient boosting machine. So a monotonicity constraint says that as one variable's value goes up, then the output of the model must also go up. Or the opposite. As one variable's values go up, the output of the model must come down. So that would be an example of a constraint. And I would say that explanations work best when paired with constrained machine learning models or these interpretable variants of machine learning models that I brought up earlier, and I gave examples of GA2M and scalable Bayesian rule list. I think if you are using a very complex, unconstrained machine learning model, and then you're hoping to squeeze some explanations out at the end, that is a recipe for failure. And that's probably most of what Professor Rudin in her criticism was focusing on, was most worried about. And I think it's very fair to be worried about that. Unfortunately, using an approximate explanation technique, something like LIME, that is available in open source software today, with a very complex machine learning model may result in simply wrong explanations, and people might not understand that they're seeing wrong explanations. So again, I want to focus on the idea of pairing post hoc explanations, techniques like LIME or Shapley that are available today, with constrained or interpretable models. I think that's a winning combination. Okay, so this Shapley value. What is a Shapley value? So Shapley values are a method for saying, and particularly, I think it's helpful to think of this in the context of credit scoring. So in the United States, I imagine there's something similar in Europe. If I apply for a credit card or for a loan, and I'm denied, very likely by a logistic regression model, very likely by kind of a statistical model, but sometimes by a machine learning model these days, the lender is required to tell me at least 4 reasons why I've been denied, okay? And those reasons are based on the columns in my data set. Your credit score is too low. Your savings account balance is too low. Your debt-to-income ratio is too high. Your length of credit is too low. Those all would have been columns in my data set. And Shapley values are a Nobel Prize-winning way to attribute how the decision was made accurately across the columns of your data set. So Shapley values is an idea that comes from game theory. A Shapley value was used originally to say how much each person contributed to the outcome of a game when the people are allowed to cooperate. And this is a really hard question because in a game where people can help each other or hurt each other or help and hurt each other, it's really hard to understand the impact of any one person in the game. And I don't think this is the appropriate venue to get into the exact details of how this works, but I'm happy to talk to you about that afterwards. But Shapley values are an accurate way to understand the contribution of each person to a game, even when people are allowed to cooperate. This idea ports to machine learning by thinking of each row of a data set and the prediction of the model associated with that row as a game. The columns that are in the data set and reflected in that one row of data are the players in the game. And so Shapley values can tell you how much each column contributed to the outcome of the game or the prediction of the model. And then that maps very nicely back to this idea of telling people why a model made the decision it made. The most important reason that we can't give you a loan today is because your credit history isn't long enough. The second most important reason is because your debt-to-income ratio is too high. Shapley values help us take apart a decision and describe it in terms of the columns in the data set very accurately. I think one thing that's really interesting to point out is that Shapley values were invented in 1953 and found their way into machine learning in 2017. Machine learning has also been around for a long time, so it's just kind of curious that such an important idea about explanation that was available to the community would have taken so long to filter into our day-to-day work lives. Okay. So another thing that's really important to talk about, I think I'll do this slide first, is that trust and understanding, I think they're different philosophies. They're different sort of philosophically. I'm not a philosopher or an ethicist. I'm not trying to, and I'm not trying to be. I'm a technologist. But I think, through some very, very simple arguments, I think I can convince you that they are different. So who in this room understands how a suspension bridge works? Anybody, any structural engineers here? Okay. Who has driven your car across a suspension bridge? So I have, okay? So I don't need to understand the way the suspension bridge works to risk me and my family's life to drive a car across it, okay? So trust and understanding are different. I can trust things that I don't understand, and I can certainly understand things that I don't trust. And these are the techniques in the workflow. And I think some are more aligned with trust, and some are more aligned with understanding. And okay, so now maybe let me show you a technical example, but before I do, I just want you to think about this. I think that some techniques are more aligned with trust, and they tend to cause understanding as a side effect. Okay, if I really test my model and really start to trust it, if I really rigorously test my model and start to trust it, during that testing process, I will have come to understand certain things about my model, okay? So, same works for understanding. When I understand something really well, as a side effect, I may start to trust it, okay? I also, as a side effect, may decide my understanding of it makes it untrustworthy. So let me give you an example of that. That's what this slide is. Okay, so this is a fairly technical argument, but I think many people in the room will be able to follow it. On the right, we have a variable importance chart generated by Shapley Values, so it's accurate. It's not inconsistent, like a typical variable importance chart would be. So we can see that there's this feature, pay zero. Someone's most recent repayment status is very, very important to this model, probably too important, as we'll see. So the other chart on the slide are the residuals of the model plotted by this variable, pay zero, someone's most recent repayment status. So on the bottom row are the good values of pay zero. So things like you paid off your balance completely, you paid your statement balance but left some charges left on the card, you made your minimum payment, or you're just 1 month late. That's the bottom row, okay? And what I want you to notice on the bottom row is what's really driving the error. The large values are in green. They're high positive numbers, okay? The upper rows are bad values of pay zero. These are people who are very late on their most recent repayment. And the large values there are blue. They're negative numbers, okay? And so what this tells us is when pay zero has a good value, but I am wrong, the model, no, I shouldn't say I, when the model is wrong, this causes large positive residuals. So what's happening here is someone makes all their payments, or makes their most recent payment, which you can see the model really keys in on. They make their most recent payment, but then they default the next month. And that causes large errors, those large green residuals. The other option is that someone missed their most recent payment, but then makes their next payment. And that's the top rows. So what's gone on here is this model is too focused on their most recent payment. And because of that, it experiences large errors when that most recent payment isn't indicative of what happens next. So I've explained to you what's wrong with this model. And I would not trust this model to do credit scoring. I would not use a model like this to do credit scoring for like a $1 billion lending portfolio. That would be a horrible mistake. So we can understand things and not trust them. Even very technical machine learning models can be understood but not trusted. Okay, so moving on in our workflow is the idea of model debugging. All right, and this gets to something that I said earlier that I do believe is that we have these measurements like lift and AUC and MSE and BIC. You know, the list goes on and on and on. None of these things tell you if your model is actually fit for use in the real world. So model debugging is an emergent discipline that focuses on testing your machine learning model as a part of a realistic component in a complex IT system. Okay? And I think this is crucially important, and it's not done very often yet. I think it will be done more often in the future as people understand the horrible mistakes that can be made. And so this involves testing your model for being secure, which we'll go into more details on in just a second, for being fair, which is probably the next box down. I've separated them in this presentation, and being truly accurate, okay? So that same model that I showed on the previous slide has another problem, and I only understood this when I did some model debugging. That same model, because it's so keyed in on pay zero, if you miss your most recent payment, it doesn't matter if your next payment is $1 million. It will still say you're going to default, okay? So that's a logical error, because you can make a payment greater than your credit limit, and this model will still say you're going to default. That's a logical error that I was only able to understand by testing the model very rigorously, putting it through many simulation scenarios, and discovering that the model actually has logical errors. So if we think about a standard random forest model or gradient boosting model, it's not uncommon for these models to have hundreds of thousands of rules. You think all those rules are right? They're not. And that can cost you money. That can cost people's lives. So we really need to test these systems very rigorously. And let's talk about security. Let's talk about security now. Okay, so I know this is hard to read. Like I said, hopefully you'll have access to the slides. If not, I have this on the internet. It's on my GitHub. I'll give it to you on a thumb drive, whatever you want. Come see me. So there are specific attacks that can be conducted against machine learning models. Now, if you're at a bank or another large company with a competent, well-functioning security division, you probably have bigger things to worry about, today at least. I don't think hackers see this as their first option today. But as machine learning becomes more and more prominent, these attacks might also become more and more prominent. And there's essentially two kinds of attacks, okay? One attack is more of an insider attack, and we tend to call that data poisoning. Data poisoning is when maybe someone inside the company, or someone who's able to get access to the training data without proper authorization. So just someone can get access to the training data. That's the first step in a data poisoning attack. And what they do is they change the training data, potentially very subtly, so that they have the outcome that they want from the model. So if I'm a data scientist at a disorganized fintech startup, it's actually arguable whether it's even illegal for me to change the training data to get my girlfriend or my boyfriend or my mother or whoever it is a giant loan. Okay? That might not even be illegal. And Lyft and AUC won't tell you anything about that. The other kind of attack basically is manipulating the model from the outside. So data poisoning is manipulating the model from the inside. Other kinds of attacks basically involve manipulating the model from the outside. And that may be as simple as finding a weird row of data that tricks the model and gives me the prediction I want. That's known as an adversarial example attack. It may be more sophisticated and actually be able to extract the logic of your model through the prediction endpoint. And it can be as damaging as reconstructing every single row of your training data, okay? So if your machine learning model is exposed but requires authentication, has some kind of throttling or protection where someone can't hit the API repeatedly, very quickly, then these attacks are harder to do. But these commercial services that allow you just to put a prediction API up at some open endpoint, you're basically just giving away your training data to somebody that knows what they're doing. So it's very important that we think about basic common sense security elements when we're exposing our machine learning model to the world, because people can manipulate the system from the inside and the outside, potentially as damaging as reconstructing your training data. And that's what's known as a membership inference attack. Okay. So sometimes I talk about disparate impact as part of model debugging. Sometimes I talk about it as its own topic, and it probably warrants being its own topic. So probably a lot of people have heard about ethical AI or unfair AI, and this is a very thorny, difficult subject. So I like to talk about it in the context of something known as disparate impact, which is encoded in regulation in the United States. It's a little bit easier to talk about something so complex and potentially personal to people when we're talking about something that's just what the law says. So roughly in the United States, the concept of disparate impact or adverse impact says that we don't want the model to treat any one group of people more than 20% differently. Okay? Now, of course, the reason things get so tricky here is in a medical application, we might want to treat different kinds of people differently. But so this idea refers to things like credit lending and employment, some insurance transactions. We want the model to be blind to things like race, gender, marital status, disability status, and hopefully we can all agree that that's a pretty good idea. So there are fairly easy tests that you can do today to look for glaring bias problems, okay? And they're known as disparate impact testing, and I've put some tools up on the screen that you can use to do this today. There's been a lot of research in this recently, and new tools sort of give us three options to address these problems. We can pre-process our data, change our data somehow, weigh it, sample it in a way that presents itself in a more equally distributed way to the machine learning model. One thing that's very interesting to me, another option that I think is perhaps the best option, is to train models directly that are sort of blind to certain social attributes. I think that's the most appealing. And the third option is to post-process the decisions that the model makes so that they're more fair by some definition of fairness, some mathematical definition of fairness. So we can pre-process, train fair models, or post-process our decisions today, in addition to testing for unfairness. So there are free open source tools that allow you to do this today. And if you are deploying a machine learning model that's going to be affecting human beings, I think it's your responsibility to do this. It's not that hard. The one thing to be aware of is that a lot of especially the disparate impact testing tools, were sort of built with the idea that people would be using linear models. And machine learning models, while they very rarely make up bias that's not in the data, they do exacerbate bias in the data by making it more difficult to find sometimes. And so the only warning I have here is that if you're using a very complex machine learning model, which again, this might be an argument for why to use a constrained model, would be that a very complex machine learning model might hide or exacerbate bias in your data in ways that would be difficult to test for. And how you test for that is, it's kind of an Easter egg hunt. I don't think anyone yet knows today how to test for machine learning models sort of hiding bias in very complex ways. Okay, maybe this is an easy one. It's a time-consuming one. It's a boring one. But models should be documented and reviewed by human beings, okay? Especially high-stakes models that are going to be making decisions about people's lives or lots of money. All right. This is incredibly important. We could do a whole 2-hour talk about any of these pieces, and this piece is the same. But the thing I like to emphasize to people is, and especially to my students, when you're a data scientist, typing on your MacBook with all your cool stickers on it, writing your beautiful Python code, sadly, you're just costing your company money, or your employer, whoever it is. The only way the things that we do are well, that's not true, but one of the main ways that the things we do are impactful and actually make or save money or drive value for an organization is when we take the model off of our laptop and move it into some kind of large, complex production IT system that's exposed to the public or exposed to people being able to use it in some way. And that's a very difficult, complex process, and I think the only thing I want to emphasize in the amount of time that we have left is that deployment introduces even more complexity into a machine learning workflow. It's a crucial part of the machine learning workflow, and fairness, security, and accuracy are not static. okay? So sadly, just because I tested my model for all of these things today doesn't mean that even if it looks great today, there might be a problem tomorrow, okay? Because the data changes, the environment changes, the market changes, and most machine learning models are just trained on snapshots of data. And as the market changes or the environment changes, their predictions become stale, and they can become less accurate, more unfair, or maybe security conditions change. So all of these things need to be monitored for in real time. Okay. Crucially important part of the workflow, and not something that I see particularly often. If you're going to be making decisions that affect people's lives, you probably need to give them a way to appeal a decision. Who here thinks that machine learning models are always right? So, I'm glad no one raised their hand. So, they're not. They're probabilistic models. And human beings are not always right either. And of course, the hope is that the machine learning model will be right more often than the human. And that, I think we've seen that proven to be true in some cases. But machine learning models are going to be wrong. They're going to make wrong decisions about people. So today in the United States, machine learning models are used for high-stakes decisions like lending, employment, assigning people bail, so how much money they need to pay before they get out of jail before a trial, how long their jail sentences might be or their prison sentences might be. And unfortunately, in 2016, there was a documented case of someone being denied parole, being kept in prison by a proprietary black box data-driven system. And it turns out the reason he was kept in prison is because his data was wrong. And because it was a black box, there's no way to logically appeal a black box, okay? So explanation and interpretable models enable understanding, which very crucially enable appeal of model decisions, okay? So if you are going to be deploying a machine learning model that makes decisions about human beings or other high-stakes decisions, I think it's incumbent upon us to make those decisions appealable, okay? And again, I don't know how to appeal a black box. And you know, people will argue with me about this all the time, and I've probably told this story 5 times since I've been in Hungary, or I've told my little joke. If, you know, a self-driving car ever crashes into, say, a McDonald's or a Burger King, do you think the attorneys for, you know, that large company are going to say, "Oh, you were using deep learning? That's so cool"? No, they're not going to say that. They're going to say, "How does this work exactly?" "Oh, you don't know?" Well, you know, we'll see about that in court, right? So this idea that cool black box machine learning, deep learning systems are just going to be working all over the place, and in places like Europe and the United States with incredibly complex regulations is absurd. I think it's just absurd. It's a scam. So keep that in mind. I could be wrong, but you know, these systems have to work in the real world, and the real world is very, very complicated. We know these systems can be wrong often, and so the least you can do, I think, is make them appealable. Okay. Decommissioning a model is the idea of, I don't just delete a model when it's done. A model that's used for some kind of high-stakes decision, I don't just delete it when I'm done using it, when it becomes stale. I have to preserve it. It has to be executable. What if there was a security problem with it? What if there was a fairness problem that's being litigated with that model? It can't be deleted. So these models are going to live forever, or they're going to live for some legally determined amount of time. We don't just delete a model when we're done using it. So keep that in mind. Okay, and the last point I'll make here, because I know the timer came on a little bit late, it's fine, no big deal, is that we need to think about not just accuracy when we're thinking about how to improve a system, okay? So data science is very iterative, and very often we tend to think of those iterations as ways to improve accuracy. But it's also a good idea to think about an iteration in our workflow that improves fairness, or improves security, or improves privacy. Those are very important and perhaps more important improvements in the real world than a slight improvement in accuracy. Okay. These are big ideas. There's a lot of open conceptual questions. I want to leave some time for questions from the audience, so I'm going to just show these very quickly. And these are some of my materials that you might find helpful. And then there's just lots of references here if you want to follow up on any of the things in the slide that you found particularly interesting. I think the last thing I'll say is, don't try to boil the ocean, right? I mean, it's not like the machine learning systems I make can do all these things. So I want to be very open about that. I think it's important to key in on the parts that you feel are most sort of impactful to you or impactful to your customers and focus on those first. You don't have to do all of this at once. And again, I want to say that the machine learning systems I'm responsible for aren't able to do all these things today, but I hope that they will be in the future. All right, so with that, let's take some questions if there are any.
All right. Yeah, I think we have time for one or two questions. We can bring them up. All right. You talk about a typical feature importance representation not being accurate. What causes this inaccuracy?
Let's see. Okay, here's a major thing that would cause feature engineering not to be accurate. The data changes. So I make my machine learning model. It's beautiful and perfect on my laptop. I ship it over to IT, and 8 months later, it gets deployed. Okay? So if you have some feature that's very keyed in on what was going on 8 months ago, say that was Christmas time, and now your model's being deployed in the late summer, that feature's useless and inaccurate.
All right, we can have one more question.
Okay.
How about, what is the biggest threat we face with the current usage of machine learning?
Oh, wow. My biggest worry as someone who is very driven by machine learning in my professional life is just that something really bad will happen, whether that will be caused by a hack or some kind of unfairness or disparate impact problem or just inaccuracy problem. My fear is that there will be another AI winter, and I don't know if people are familiar with that term, but this is maybe the third or fourth time that AI has been extremely hyped since the 1950s, and every single time before it's failed. So I don't want that to happen again, and so that's why I think it's incumbent upon us as practitioners to do the responsible thing and make sure that our systems are accurate and fair and secure.
All right, thank you very much. One more round of applause.